If you were to employ the techniques you learned in Inorganic Chemistry 1 to draw Lewis structures, it would take about a week to finish the Lewis structure for this molecule. Counting valence electrons is not necessary in organic chemistry if you keep in mind these facts. Carbon forms 4 bonds with no lone pairs. Nitrogen forms 3 bonds with 1 lone pair. Oxygen forms 2 bonds with 2 lone pairs. Halogens form 1 bond with 3 lone pairs. Halogens being fluorine, chlorine, bromine, iodine. Looking for functional groups in my molecule, I notice this pattern, which is RCHO, which we have learned is an aldehyde. If you look carefully in this direction, we have a carbonyl attached to an O attached to a C, which we called an ester. Similarly, we have an ester in this direction with the carbonyl on the left this time. The parentheses in the middle of this formula indicate that that group inside the parentheses is sticking off of the previous carbon. I think we're ready to start drawing our structure. I'm going to start with a string of atoms that is overly long. I'm going to draw my aldehyde on the end, which has a carbonyl attached to a carbon with an H. Next carbon in has 1 bond to H. My computer thinks it is smart and fills in octets for me, even though I have not asked it to. The next carbon in has no bonds to H. The one after that has 1 bond to H, as does the one after that. 1 bond to H, 1 bond to H. Clearly, I'm going to have to fix the carbons again. This carbon corresponds to this carbon. That is the carbon that is part of the ester functional group, which means it is attached to an oxygen, which is then attached to a carbonyl, oxygen, carbonyl, which is attached to a carbon with a CH that is a CH3. Molecule needs to be moved a little. Fixing labels. Keeping in mind, a Lewis structure must show all bonds. You are not allowed to write CH3. I will be doing lone pairs on oxygen later, as I will also be doing pi bonds on carbon later. We're up to this juncture here with this carbon being this carbon. It is attached further on in the chain to this carbon here, which is attached to a carbon. Both of these have no bonds to H. Then we come up to the carbonyl of the next ester, which is followed by an O to make it an ester. The O is attached to a C with one bond to H, which is attached to a C with two bonds to H. Clearly this is all extraneous now. Here's my C and my other C, and these are H's. Keeping in mind carbon always forms 4 bonds with no lone pairs. We have issues with this carbon here having only 3 bonds, and the carbon next to it having only 2. The carbon on the left will be fixed after I make a second bond. Keep in mind that H does not belong, but the carbon on the left now has a full octet. Carbon on the right only has 3 bonds, which needs another bond to the one on the right. That H is not there. I have issues with an sp carbon not being drawn linear. I will fix that shortly. Moving to this carbon here, clearly it needs a pi bond. Do not do it to the left. You will have an octet violation to the left. Do it to the right. And keep in mind those H's do not belong. We need a third bond from these two. And octets are all full there. I'm going to take advantage of my program knowing that those should be linear carbons when they're sp. And there we have it. It redrew it a little better for me. On the test, I will not give you trouble if you have bent bonds, because initially you don't know if they're supposed to be linear or bent. I clearly need some lone pairs for my oxygens. Wow, sorry. It's not letting me move things very nicely. You can laugh as you go. I'm laughing. There we go. And we have 2 more lone pairs necessary for the oxygen to the far right. I'm thinking these are fine. I will continue this problem on the next video portion. I'm not quite finished. As you see, the carbon on the right needs a pi bond right here, and we will stop here and continue on the next video.